Hello, hello. Hope everyone's doing well. Let's talk about all things fat related. So we're going to start off just in like an overview of fats, cell membrane, phospholipids. Then we're going to get into lysosomal storage diseases, cholesterol, how it's made, how it's regulated, and what it's good for. A couple things that it is good for. One is making adrenal gland hormones like cortisone, aldosterone. It also helps make bile acids. So we'll talk about that and the synthesis and breakdown of bile acids. Bile acids combine with something called bilirubin to make bile. So bile acids are not bile; they are a component of bile. So, as long as we're talking about bile and bile acids, we'll talk about bilirubin. So we're going to talk about bilirubin, which is really just a heme breakdown product, and when it accumulates, you get something called jaundice. And if we're talking about bilirubin, which is heme breakdown, we might as well talk about the heme synthesis and what happens if it goes awry, which are the porphyrias. So yeah, I know all of this seems kind of weird. But there is a tether between all of these things. It kind of reminded me of Yoda a little bit. But fats remind me of cholesterol, and cholesterol, those go to bile salts. Bile salts are going to combine with bilirubin to make bile, and bilirubin is the breakdown of hemes. We can also talk about the synthesis of heme. And again, we're going to talk about the adrenal cortex hormones and this, which I absolutely hate, but it's got to be done. All right, fats. So general breakdown of fats. Most people just think of fats. They're probably thinking about triglycerides. These are in adipose cells. But a lot of what fats are good for is going to be in the membrane of cells. So we have phospholipids, which is probably what you're more classically familiar with. I guess most people say phospholipids, they're thinking glycerophospholipids. Notice glycero. We also have sphingophospholipids, emphasis on sphingo. So really the main difference between these is they have different backbones. We can also slap a sugar on it. It can be a glycolipid. So here we have a glycerol, two fatty acids, a phosphate, and some X group. I'm just going to call it an X group. And this is very similar, but instead of glycerol, we have a sphingosine. Notice that one of the fatty acids is just intrinsically part of the backbone. So you're only ever going to put one fatty acid on this. And again, we have a fatty acid, phosphate, and some X wild card group. Then we have globosides and cerebrosides and things like that. This is glycerol. Everybody should be very familiar with this. These three carbons attached each to a hydroxyl group. Fatty acids, so we can have just saturated fatty acids. Saturated means full of, like a saturated picture, saturated with colors, full of color. And so this is full of hydrogen, so no double bonds. Unsaturated, even just one double bond makes it unsaturated. They're typically cis. It can be trans, like a trans fat. If you hydrogenate it, this is artificial and it's unhealthy. You can also imagine if we had several of these, you could stack these on top of each other really well. There's going to be a lot of van der Waals interactions. There's going to be a high intermolecular adhesion, and therefore a high melting point. So that's why this is something more like butter. These do not stack as well. If you wanted to, stack this on top of each other, it doesn't stack quite as well. If it doesn't stack, there's less attraction. It makes it more likely to be a liquid, and therefore this is an oil, the unsaturated fats. So if you put on 3 of these fatty acids on a glycerol and you get a triglyceride, this is going to be stored in adipose tissue. All right, so if we want to break down a fat, and this just happens, both artificially and naturally. Let's say that I haven't eaten in a while and I've got a couple extra pounds on me, and it's important that I give energy to my brain, so my body's going to start breaking down my fat. And so how does that work? Saponification. I'm going to take these, these 3, emphasis on the 3 OHs, are going to attack that. And then that's going to go over there. And that's going to give us just a glycerol and a soap. We call this a soap because this R group is just going to be kind of like a bunch of carbons. And then we have this, this carboxylate group. So this is going to be nonpolar, and this is going to be polar. Whenever you have a polar and a nonpolar thing, that's amphipathic. It's a detergent. We can call it a soap. Now that really just what we just saw kind of really just describes, if anybody's seen Fight Club in a nutshell, they steal a bunch of fat from people in people who've gotten liposuction from plastic surgeons. They steal the fat from the clinic, and they have a bunch of lye, which is just a strong base. You put those together, and it's saponification. They make soap, and then the joke is that they sell it, back to the people who were getting the liposuction in the first place, and they have the glycerol. Glycerol is glycerin, and you combine some nitric acid, and you got yourselves an explosion. So the cell membrane, we say, is the fluid mosaic model. It's fluid. It's kind of fluid, kind of stiff. It's it's this Goldilocks zone of perfect fluidity, and it's a mosaic because it's kind of like a cookie where you have little blueberries or raisins or chocolate chips and nuts and stuff just put randomly in. So we have these things, but of course the main component of the fluid mosaic model is the phospholipids. They are what give it this very unique, not too stiff, not too fluid thing, and allow things like endocytosis and exocytosis. Seen here. So of course we have the hydrophilic head interacting with all of the water, and on both sides it is a bilayer. And in here we have our non-polar region, all of the fatty acids interacting with one another. And of course, this is why things like sodium are not allowed through like this. They would have to go through a transporter. Small things like O2 and CO2, of course, can just diffuse right through that are non-polar. So we have this glycerol. Always be able to find the glycerol, 3 carbons, each attached to an oxygen. One fatty acid there, another fatty acid there. Sometimes they're saturated, sometimes they're unsaturated. The more saturated, like we saw earlier, is going to make a stiffer membrane. Longer is going to make a stiffer membrane. Shorter and unsaturated is going to make a less stiff membrane. And here we have this, a phosphate with an R group or an X group or a wild card, which can be a whole bunch of different things. And we really just see the same thing over here. This is our X group, and let's actually talk more about these. We talked about this a bit briefly last time. So, sometimes they're hydrogens, but it could be ethanolamine or it could be choline. Remember that CH for the methyl groups, and this is something that we needed in myelin, and we needed our B9 and B12 for, et cetera, et cetera, et cetera. And an inositol, which we'll come back to later. And this is just, boom. We can find the glycerol right here by seeing this. These 3 each attached to an oxygen. So this is glycerol. This is sphingosine up here, up top. Notice that we have the 3 carbons is the backbone, is the way to really make the link. We have an OH here and an OH here. The second OH is actually an NH2 in the sphingosine. And the third one, the OH is put up versus put here. That's actually the same. The difference is that this is the end of the road for this carbon right here. Well, this carbon right here actually has a long fatty acid intrinsic to the backbone. So a sphingolipid, again, there's the sphingosine backbone. You're going to have one fatty acid and typically an X group. And just like earlier, the X group is a wild card. If it's just a hydrogen, we call that a ceramide. But you can put lots of things like choline, ethanolamine. A lot of the X's between the glycerophospholipids are the same as the sphingospholipids. If you put one single sugar, like glucose, it's a cerebroside. If you put 2 or more, it's a globoside. And if you have several sugars and one of them is a sialic acid, that is a ganglioside. Here's just a picture of all of these. Notice the ceramide has really nothing attached to the X group. The X group is just a hydrogen. The sphingosine here is just the backbone. Both of these are counted as sphingomyelins, whether it's a choline or an ethanolamine group. One sugar is a cerebro. Several sugars with a sialic acid is a ganglioside. They're really important in the cell membrane, but they're also important for signaling, intracellular signaling and between cells signaling. So a couple different ways the GPCR pathway can go, and an RTK. I think there's a little bit of overlap between these, but you could have a heterotrimeric G protein. Once activation occurs, the G alpha gains a GTP. It's activated. It separates from the G beta, G gamma. It can go over and it can interact sometimes with the adenyl cyclase, but it can also interact with phospholipase C. Phospholipase C, I always thought of C for interacting with the inositol with the 3 phosphates. So this is inositol phospholipid. So it's a cell membrane phospholipid. And we know that we've seen this again and again. We have this phosphate group here, and it's attached to the X. So the X is the inositol, and it's attached to 2 other phosphates, like this. So this is the phospholipid, and here's the X, which happens to be attached to phospholipid number 1 and phospholipid number 2, which is why they call this PIP2, because it's the P linking the X group, the inositol, which happens to be connected to 2 phospholipids. Now, it just so happens that phospholipase is, you can imagine it's a lipase, it's cutting a phospholipid. It actually cuts right here. So at the end of the day, you get all 3 phospholipids on the inositol, and that's what we call, after it's left now, IP3. IP3 is a signaling molecule. It goes over to the endoplasmic reticulum, the smooth endoplasmic reticulum. It opens up the ligand-gated calcium channel, and it lets all of the calcium out, which is going to activate other things. This is just another picture of this. We have fatty acid number 1, fatty acid number 2. This is our glycerol. This is the phosphate group that is linking our X. Here's our X thing, which happens to be an azotol here. It has 1 phospholipid and 2 phospholipids, but because we're cleaving it here, we actually count this as the 3rd phospholipid. We call that IP3 now. DAG is diacylglycerol, which is what's left over. And this kind of makes sense. Acyl group is really just like a fatty acid, and we have 2 of them. And there's the glycerol, hence the G. So we can also use this as just signaling in the plasma. Important one is arachidonic acid. So we're going to have these esterified in the cell membrane. Phospholipase A2 can free up an arachidonic acid. Notice that things like prednisone and cortisone, a lot of the corticosteroids are actually going to inhibit this. So we'll see later that corticosteroids are anti-inflammatory. They're suppressing the immune system. This is one of the ways which they do that. They're going to stop this process. So arachidonic acid can become, if we look downstream, it can become several things. We're probably mostly familiar with this in life just from, you got a headache or you've got inflammation. You're going to go ahead and take like Advil or an aspirin or something like that. And that's because something downstream of the COX-2 pathway creates a pro-inflammatory prostaglandin. And so we want to take aspirins or NSAIDs or COX-2 selective inhibitors to stop this. Now, the problem is that other than these are actually, again, COX-2 specific, but the aspirin and the NSAIDs actually also are going to inhibit COX-1. COX-1 is, again, we can see it makes a whole bunch of stuff. One thing you might have heard is that you can't take like Advil every day, or you might get like stomach ulcers. And that's because you need mucus to line your stomach because of all of the acid. And COX-1 is going to help make that happen. So if I'm taking Advil every day because I don't like the pro-inflammatory COX-2 downstream product, well, there's actually a little bit of crossover. We're also inhibiting COX-1, which is just trying to do a lot of things, one of which is protecting our stomach. All right, let's jump into some lysosomal storage disease disorders. Personally, I always like as much as I can to make intuitive sense of everything and build a strong foundation. But I'll just be straight with y'all. These just suck. There's not a lot of rhyme or reason to which disease has which phenotype or, the pathophysiology behind them. So I am honestly just going to be regurgitating a lot of first aid to y'all. So I don't really have a lot to add here. These just suck, and you just got to memorize them. It's sort of it's a rite of passage. So start off, I would take a mental snapshot of this. This is going to be really important. If you understand this, it's going to make everything a lot easier. But a lot of what we're doing is just going to be going through mnemonics to maybe help you pick up a buzzword here or there. This is when there's a problem of breakdown of these sphingolipids or mucopolysaccharides, which we'll see in these two diseases. And they can't properly get broken down, and the lysosomes swell, and it causes a lot of issues. So for the sphingolipids, we have Tay-Sachs, Niemann-Pick, Fabry, Crabbe, and Gaucher. There's actually a couple more, but those are the main ones. And then for the mucopolysaccharides, we have Hurler and Hunter. All are autosomal recessive except for Fabry and Hunter. So Tay-Sachs, I think of a small gang of 6 people. The 6 is to remember that the deficient enzyme is hexosaminidase. We're going to accumulate ganglioside. This disproportionately affects Ashkenazi Jewish populations. And it's important to remember that this is a small or really a normal size spleen that's going to differentiate it from Niemann-Pick, which we'll get to next. It causes neurodegeneration. Again, all of these diseases we're probably going to see pretty early. So it's not like a 42-year-old woman or man is walking into your office and it's an issue. Someone's coming in and saying, hey, we think there's something wrong with our 3-year-old son. And you get this cherry red spot on your macula, which is at least is going to narrow it down to either Tay-Sachs or Niemann-Pick. So Niemann-Pick, you pick your large nose with your foamy finger. To the sphinx, to remember that it's a sphingomyelinase deficiency, which means, typically things are named after the precursor. So if we don't have sphingomyelinase, then we have sphingomyelin. And it's a large finger. It's a large spleen. That is really how you separate this from Tay Sachs. Additionally, there's these foam cells, which are enlarged macrophages in the Niemann-Pick. Also neurodegeneration, also cherry red spot on the macula. Gaucher's disease. So I just remember that the GC separated by 2 letters. And this is both the enzyme and the thing that builds up. So again, the enzyme, it makes it easier if you just remember that the enzyme is almost always named after the precursor. So here we have this and this with 2 letters, and this with 2 letters. Again, this is not my favorite way of teaching, but there's just not a lot of rhyme or reason to these. So however you can stick it in your head, that's the way to do it. Causes osteoporosis, especially the femur for some reason. You get lipid, so a buzzword you might see is lipid-laden macrophages that resemble crumpled tissue paper. I actually have seen that in a question, which is kind of nuts. Disproportionately affects Ashkenazi Jewish populations as well. Fabry, I thought of someone who uses like Fabry softener as like a hoity-toity person. And galactositis A, they always need the finest things in life, only the A's. Someone who has a bunch of ceramic vases is hoity-toity. So this is the accumulated structure, cerama and trihexoside. And if you're very fancy, you know what? You probably play the harp, HARP. Hypohidrosis, you can't sweat. Angiokeratoma, you can see here. Renal failure and peripheral neuropathy. Again, how does it cause all of these weird hodgepodge of symptoms? No idea. Wish I did. Crab, so I think of like, taking a bite of crab and being like, dude, this crab is out of this world. This is so tasty. Out of this world, I think of like a galaxy. So galactosebarosidase. And again, you're named after the precursor. So if the enzyme is not working, what's going to build up is you're going to have a buildup of this galactosebaroside. Again, out of this world. It destroys oligodendrocytes, which are going to myelinate things in the central nervous system. And so you can get optic atrophy. So the optic nerve is heavily myelinated, so you can have vision loss. Also peripheral neuropathy, which seems a little bit weird because we are talking about the oligodendrocytes, which are in the central nervous system. But even if you demyelinate the central nervous system, it can still actually cause peripheral neuropathy, even though that's not the main mechanism. And a globoid cell, we can see here. I just think of taking like a big globule of crab meat. Metachromatic leukodystrophy. So meta, I think of, thinking, and this can cause dementia. And then dystrophy, think of muscular dystrophy, which is like, it's a peripheral issue and it's severe ataxia. People have trouble balancing and walking and coordinating their movement. So that's how I remember that it's the CNS and the PNS. And some things like meta, it's like you got to use your cerebrum. And so it's a cerebroside that is accumulating. And the enzyme might seem like it doesn't have anything to do with the accumulated structure, but it's a cerebroside sulfate. And this is the sulfatase. So that's the way that you can maybe make the connection. All right. So yeah, those are all the lysosomal storage disorders involving the sphingolipids. What about the mucopolysaccharides? So we have 2. We're going to have hunters and hurlers, and we're going to use hunters and hurlers like as a concept or as an analogy. So for the hunters, it's iduronate 2-sulfatase. And for the hurlers, it's alpha I don't even know. But I just remember that the alpha, you have to be like an alpha to hurl a heavy, boulder. So I think of like a classic hunter, and then somebody who's hurling boulders. I don't know. I thought of like the Cyclops from the Odyssey. You've got to be a real alpha, real strong, be able to hurl a giant boulder like that. Both of these accumulate the same structure, heparin or dermatin sulfate. They can both develop gargoylism, but the hunter phenotype is a little bit less severe than the hurler phenotype. And I just thought of, most hunters would have facial features which are more quintessentially, average or human than a cyclops or a giant who might have more coarse facial features. And so that reminds me that the hunter phenotype is a little bit less severe than the hurler phenotype. But to be a hunter, though, nevertheless, you do have to be quite aggressive. So very aggressive behavior that we see with the hunters. X marks the spot. So the hunter is going to be X-linked, while the hurler, as most of them other than Fabry, are autosomal recessive. And the hurler has corneal clouding. And I just thought of, if you're throwing a giant rock, you don't really need to be that, your aim doesn't need to be perfect, right? To be a hurler, you're just throwing a big boulder. But to be a hunter, you probably need your vision a little bit more. So the hurler doesn't need the great vision, the hunter does. hopefully, yeah, go ahead and memorize a lot of this stuff. This section just really sucks. Okay, another very important type of lipid is cholesterol. Most people just think of cholesterol and think, oh, cholesterol bad. You want to have a low cholesterol. Maybe you're a little bit more nuanced, and okay, well, you want the HDL high and the LDL low, but cholesterol actually is a whole bunch of roles to play in the human body. So first of all, this is, of course, cholesterol, and you should be vaguely familiar with the structure. These 3 cyclohexanes, 1 cyclopentane, the hydroxyl over here, and then this little aliphatic chain over there. The pathway for, I would know that acetyl-CoA at the end of the day is going to become cholesterol. And I would know that the rate limiting step, one of the earliest steps, is once we have HMG-CoA, the enzyme HMG-CoA reductase acts on that. Because it's the rate limiting step, it is highly regulated, and the drug, the statins will inhibit this. So if someone's cholesterol is too high, then you can take a statin, and that inhibits this enzyme, and you produce less cholesterol. So if we skip ahead past a lot of this, I think all of that's kind of low yield. The 4 really important things to know is membrane composition. It's one thing that it does. We can make bile acids, bile salts. We can make steroid hormones in the adrenal cortex, and vitamin D. So that's our rate limiting step. So cholesterol to vitamin D. We can get vitamin D just from our diet, but we also have cholesterol that sits in our skin, and when UV rays come in, they can just convert it into vitamin D, which goes to remember that vitamin D is not active until it's been hydroxylated twice, once on the 25 and once on the 21st carbon. So the liver will get the 25 hydroxylase, and then it'll go to the bone, or the liver for the most part, or macrophages to be hydroxylated on the first. So for the most part, it's the kidney that is doing the 1 hydroxylase. Now we have 125, and this is calcitriol, and this is the active version of vitamin D. Cholesterol can also kind of be wedged in between phospholipids in the cell membrane. This acts as like a fluidity buffer. So if we look at the no cholesterol, so let's say that this is our ideal fluidity right here at a particular temperature. Okay, what happens if I raise the temperature just a little bit right here? Oh, now it's way too fluid. All of the phospholipids are coming apart, and that's not good. Okay, well, what if we just make it a little bit colder? Okay, now we're here. Well, now it's way too stiff. Everything is way too rigid and stuck together. Somehow above my pay grade, cholesterol acts as a fluidity buffer, so that when it gets hot, it keeps it a little bit more stiff, and when it's cold, it keeps it a little bit more fluid than it would normally be without cholesterol. So it buffers against this, and it kind of keeps us in this nice Goldilocks fluidity zone. We also have these things called lipid rafts, where there'll be a high density of proteins and glycosylated sphingolipids and cholesterol, and they play a role in signaling. Imagine all of the pathways we've seen with GPCR and RTKs. There's a lot of proteins that are quickly interacting with one another. Wouldn't it be it would be a lot easier for like a GPCR to interact with a G alpha to interact with an adenyl cyclase if they were all clustered together on this little island of proteins that are kind of all tethered together. I mean, imagine having like a bunch of cans that are floating together in the ocean, but they've been kind of tied together with this twine, which keeps them as kind of like a raft together. So if you interact with one Coke bottle, all the other Coke bottles are close by, and somehow cholesterol plays a role in that. The adrenal cortex, we can make these steroid hormones, progesterone, corticosterone, and aldosterone. We have a whole section about these today. And making bile salts is maybe the last major thing. So bile salts are not bile. Bile salts are the major component of bile, but it also includes things like cholesterol and bilirubin, which is just a heme breakdown product, which we'll get to. So the liver makes these bile salts. We can store them in the gallbladder. They go into the small intestine, where they're going to interact with a bunch of fat molecules. The fat molecules, they're going to help them sort of enter into solutions. They can interact with lipases and be broken down and absorbed more easily. Some of the fats then just go out into the toilet, but some of them get reabsorbed. Really the major component, like the major thing about a bile salt is the amphipathic nature of it. Like the soaps that we saw earlier, is that it can interact both with the hydrophilic bit, the aqueous solution, but can also interact because of all of these carbon chains with the nonpolar solution. So we kind of see this here. It is hydrophobic on one side and hydrophilic on the other side, so it can interact with the fats that we've eaten and sort of bring them into solution. This is just a little picture of this. Here we have olive oil and water, and they're not miscible. And then we add a little bit of detergent, which is basically bile salt, and boom, it's making everybody play a little bit more nicely. So as we just mentioned, one of the things that cholesterol does is it is the precursor for the steroid hormones in the adrenal cortex. We have the adrenal cortex, that's the outside, and the adrenal medulla, that's the inside. And generally, whenever you see the word medulla, we're talking about deep into a structure. So in the inside, the medulla is the catecholamines. Catecholamines are epinephrine, norepinephrine, also dopamine, but that's not produced here in the medulla. We're not going to be talking about these right now. We're focusing mostly just on the GFR. So the adrenal cortex has three components: the glomerulus, the fasciculata, and the reticularis. A lot of people remember this by the mnemonic GFR, and as well as salt, sugar, and sex. So salt being aldosterone, and then you go a little deeper, and then it's sugar, that's the cortisol, and then you go deeper, and that's the sex component, that is the androgens. And if you think about the name, the adrenal glands, ad means near, and renal means kidney, so this is right next to the kidney, it's right on top of it. The glomerulus of the adrenal cortex, this produces aldosterone. The main effect here is just to raise the blood pressure, and it does this actually by raising the sodium level. So if the blood, I know this is the world's blurriest picture, but if the blood pressure falls, this gets the kidneys to secrete renin. The liver has secreted a hormone called angiotensinogen. Remember that if you hear inogen or the prefix pro, it's likely a zymogen. So this is inactive. So the blood pressure falling causes renin to be produced. Renin activates angiotensinogen and angiotensin 1. The lung, quite randomly, generates the protein angiotensin converting enzyme. This converts angiotensin 1 to angiotensin 2. Angiotensin 2 then has some direct effects, which raises the blood pressure. But it also, and more relevant for us now, it goes to the adrenal cortex, the glomerulus of adrenal cortex, to secrete aldosterone. And aldosterone is going to cause us to increase our absorption of sodium. And if you increase the reabsorption of sodium from the filtrate into the blood, via osmosis, water is going to want to follow that. It's going to want to go to where the higher concentration osmolarity is. So the more fluid going into the blood now is going to increase the pressure. And over here, we kind of have like a little nice summary here. Here's our filtrate inside of the kidney. And we're going to have aldosterone doing four things. It causes the sodium to be reabsorbed from filtrate, which is just pre-urine, back into the blood. And then water is going to want to follow that. So this is increasing the sodium of the blood. It's increasing the pressure. It's also now, this is kind of a separate thing, but it is equally important to know. It's causing hydrogen ion secretion and potassium secretion from the blood into the filtrate. The fasciculata of the adrenal cortex, this produces cortisone or cortisol. This is the stress hormone. So if you're, back in evolutionary times, which is a silly thing to say, if you're running from a wolf, or you're under attack, or you're trying to find like a new place to camp, that's a brief moment of stress. Cortisol makes sense, but we of course now just have all of these anxieties and deadlines and chronic stress, and so a lot of people have higher levels of cortisol that are just chronic instead of the acute cortisol surge, which is kind of what we evolved to have. This does a couple things. It suppresses the immune system. We talked about this earlier. It can suppress the cleavage of arachidonic acid into prostaglandins. It suppresses calcium absorption in the GI system, and it enhances gluconeogenesis and lipolysis. So it's going to be responsible for more sugar put into the blood. A lot of people know of cortisone injections. If you have back pain or joint pain or something, a lot of the pain is due to inflammation. So if you get an injection here, this reduces the inflammation. It might reduce the pain. If you have too much cortisone, this is known as Cushing's syndrome. If you have too little cortisone, this isn't always known as Addison's, but often we know it as Addison's disease. So here we have a small adrenal cortex as Addison's. Here's our normal, and here we have an enlarged one, and you can see that it's really just absolutely filled with cholesterol, and this is really because of ACTH, which we'll talk about soon. And so this would be due to maybe tumor or just general hyperplasia. So this is Cushing's. So let's talk about adrenal insufficiency first. So there's maybe 3 hormones we should think about. The cortisol, what would low cortisol do? Cortisol is going to raise your blood sugar. So if we don't have it, this is hypoglycemia. This is going to cause us to be tired, and it causes orthostatic hypotension. So when you stand up, randomly you have a drop in blood pressure. That's often associated with hypoglycemia. Low aldosterone, well, we just said there are 4 things this does. It raises the blood sodium, it raises the pressure, lowers the potassium concentration in the blood, and it lowers the hydrogen concentration in the blood. So the opposite of that, hyponatremia, just means low sodium plasma levels, low blood pressure. Metabolic acidosis is just we now have acidotic blood, and it's a metabolic consequence. It doesn't have to do with hyperventilation or hypoventilation. And then hyperkalemia, we're not secreting the potassium. Now ACTH, if this is high, and this might be high depending on whether we have primary or secondary, and we'll come to this, but ACTH, which stimulates the adrenal cortex to produce all of these hormones, especially an emphasis on cortisol, it actually comes from this precursor called so it's a zymogen, opio, like the opioid molecule, melanin, and then cordon. So it has to do, it's the zymogen, it has to do with opioids, melanin, and cortisol. And really what you need to know about this is that if you have high amount of ACTH, this originally must have come from a pro-opiomelanocortin molecule. So if I have 10 molecules of ACTH, I'm going to have maybe actually like 30 equivalents of MSH. So the idea is that the more ACTH you're getting, the more MSH you're getting. And MSH is melanocyte stimulating hormone, which is going to cause more melanin, which is going to give you like this hyperpigmentation. It's going to give you a nice tan. Or maybe not, it might be sporadic. But so people with high ACTH with Addison's disease will have hyperpigmentation. And Kennedy had Addison's disease. You can see the hyperpigmentation here. So now let's look at the 2 types. There's primary. So primary is where we just have, maybe there's a couple different ways we can have it. So we'll go through them in a sec. But here we have the cortisol and the aldosterone levels are down. And usually this just has to do with the fact that the adrenal cortex itself is destroyed. So imagine the adrenal cortex is destroyed. We're not getting any cortisol. Cortisol is actually what feeds back on ACTH to lower it. And so the pituitary doesn't know that. It just sees that there's not a lot of cortisol. And it says, hey, what gives? We really need some cortisol. So it raises the ACTH. Still no cortisol. So it raises the ACTH more and more and more and more and more and more. But it just doesn't matter. There's no cortex to respond. So a couple ways this is going to happen. Addison's disease, we would just have atrophy of the cortex. In the developed world, this is because you have an autoimmune antibodies against the adrenal cortex. In the developing world, and this is more common worldwide, where you're going to have tuberculosis is going to cause destruction of the adrenal cortex. You could have a 21 alpha hydroxylase deficiency, and this is just a congenital adrenal hyperplasia. So this was, I guess, a little bit different. This isn't necessarily destruction, but because actually in this case you have an enlarged cortex. But the extra androgens are going to be a thing. And so in males, this is going to cause precocious puberty, and in females, this is going to cause virilization and ambiguous genitalia. And we'll come back to this. This is something we'll talk about later in this section. And then also the Waterhouse-Friderichsen syndrome. So you might have acute hemorrhage due to Neisseria meningitis. Now, a secondary adrenal insufficiency, this is where the cortisol only is going to be deficient. So ACTH is down, aldosterone is still there. Okay, why is aldosterone still there? Well, aldosterone is still present because angiotensin 2 is actually responsible for the aldosterone release, while ACTH is responsible for the cortisol release. So here, 2 different ways you might have it. Pituitary ACTH deficiency. Remember that the ACTH causes A couple things, but it stimulates growth of the adrenal cortex and cholesterol uptake, the processing of this cholesterol into pregnenolone and progesterone via a desmolase enzyme, and it stimulates the zona fasciculata to release cortisol, and the aldosterone, as we said, is released from the glomerulosa by angiotensin 2, which is why it's not affected in the secondary type. And then so it could be that the pituitary itself is deficient, or it could be that the hypothalamus is deficient. The hypothalamus has the the hormone, cortisol releasing hormone. And so if we don't have cortisol releasing hormone, we also won't have ACTH. So I would just really make sure that you're differentiating between primary and secondary sources of adrenal insufficiency. So Cushing's syndrome, on the other hand. So Cushing's is we're going to have more cortisol, and it's going to cause hyperglycemia, which is going to be associated with diabetes. It suppresses gonadotropin-releasing hormone, which is from the hypothalamus, which is going to go ahead and call for FSH and LH from the anterior pituitary. In females, this is going to cause amenorrhea, cessation of menstruation, and hirsutism, where women might grow facial hair. Males, this might cause erectile dysfunction and impotence. The suppression of calcium absorption might cause osteoporosis. And there's a very specific fat distribution pattern. So there's a truncal obesity that we see here. And this is a woman before and after she developed Addison's disease. So there's a truncal obesity. They call it a moon facies. I don't know who comes up with these names. They're not very nice. And then a buffalo hump. So the buffalo hump is this fat distribution on the posterior side of the shoulders. The skin becomes particularly thin, and so this is known as stria. So we have Cushing's syndrome. This is the umbrella term. So anytime you have too much cortisol, that's Cushing's. And it's actually usually iatrogenic. So it's basically, if anybody's watched Breaking Bad, what happens to Skylar White in like season 3, season 4, season 5? She gets a little heavy. Why did she get heavy? It's because she had lupus. Well, okay, well, how do you take care of lupus? You take a lot of prednisone. You take a lot of prednisone, which acts kind of like cortisone, and it's supposed to suppress the immune system. That's why you take it. And what happens is she got a little bit large, and she effectively developed Cushing's. And so that would be an iatrogenic cause. It's probably the main cause, taking too many glucocorticoids over the counter. But it could also be due to things like adrenal hyperplasia, or pituitary tumors, or small cell lung cancer. This seems esoteric, but it's not. It's actually quite common. You need to know this. Small cell lung cancer has a paraneoplastic syndrome, which is to say like a random side effect. Where it secretes ACTH, and it secretes actually a lot of it. Cushing's disease is the more specific term. This is where specifically we have a pituitary tumor that is secreting ACTH. So we've talked about this cortisol releasing hormone from the hypothalamus, ACTH from the pituitary and the adrenal cortex. Yes, it's going to cause more cholesterol, and that's going to help aldosterone and testosterone too. But remember, it's the cortisol release is especially affected by the ACTH, and so it's the cortisol then that's going to feed back and inhibit the ACTH and the CRH. And so this is actually going to be now a very high yield thing to be able to pick out with a high ACTH versus low cortisol levels. So before we get there, maybe like let's pretend like this is baseline right here. So a pituitary is going to have more ACTH, an active pituitary tumor. It's possible to have a non-functioning pituitary tumor as well. A small cell lung cancer that is ectopically producing ACTH, a paraneoplastic syndrome, very, very, very high. And then an adrenal tumor, we have a huge amount of cortisol, but it's coming from the adrenal tumor. The cortisol is still going to go ahead and negatively feed back on the ACTH and the CRH, and so we're going to see the ACTH levels plummet. So let's go ahead and imagine if I had high cortisol and low ACTH, what would happen? Well, it seems like the negative feedback is working as it should. So I'm going to guess there's an adrenal tumor that's suppressing the hypothalamus and the pituitary. All right, so if I have high and high, well, I'm guessing then that this started it. High ACTH levels from a hypothalamic or pituitary tumors are more common, is what's causing the high levels of cortisol. And that's what we see. Okay, what about high-low? So here, I have high levels of ACTH, but weirdly, I'm not getting any cortisol. It must be that the adrenal cortex is not really working. Maybe there's like a destruction of the adrenal cortex or something. Maybe it's Addison's disease. And then What about low and low? In this case, I'm guessing that the pituitary has a tumor and it's non-functioning, or maybe the hypothalamus is non-functioning, or there's a brain bleed, or something's wrong in the brain. Here we go. All right, so the reticularis. So again, we have the GFR, the glomerulus, the fasciculata, and the reticularis, salt, sugar, and sex. This is androgens. Now, males produce androgens with the Leydig cells. So the androgen effects are actually going to have a slightly larger impact on females than males. So all of these effects that we're going to get into, though, occur for both XY males and XX females. Only some of them I'll give an exception, like if present. But other than that, they should do this for both of them. So if the fetus is testosterone, if there's enough of it, and there typically is not in XX females, it's going to help the mesonephric ducts blossom into the internal genitalia. So this is the seminal vesicles, the epididymis, and the vas deferens. DHT, which is just a derivative of testosterone, this converts the some external morphological structures into the external genitalia. So these into the penis, the prostate, and the scrotum. Now during puberty, and so again, that's going to be typically for we have a more complex picture here, which I don't think you guys really need to know. But again, the idea is that there's likely not a high enough surge from the adrenal cortex. So this high levels of testosterone are coming from the Leydig cells for fetuses. Now for the puberty, there's a surge in both males and females, and if there are penis and testes present, this is going to enlarge them. This is going to cause the growth of pubic hair and facial hair, and again, this is going to be a little bit more for males. Deepening the voice, a little bit more for males. An increased sebum from sebaceous gland, maybe is going to be equal. It's exactly hard to say, but this is what causes acne in oily skin. Now, for adults, if there's a prostate gland, this is going to cause enlargement of it, and it causes balding. It can cause balding in both men and female. So androgens can be converted into estrogens in adipose tissue. So there's an enzyme called aromatase, and it converts testosterone into estrogen. What would the effects of too much estrogen be? It's that obese men are predisposed to have extra estrogen levels, and then this can cause gynecomastia, which is just effectively breasts that are mimicking like female secondary sexual characteristics. Now the feedback pathway is too complex and not worth getting into for y'all for right now. But obese women are actually predisposed to the opposite. They have excess androgens because if they're overweight, and so it's going all of the features that we just saw here. I made a big deal of saying they can affect females as well. They're going to balding, acne, oily skin, deepening of the voice, and facial hair. I always thought of like facial hair. I thought of hair and hers. Helps me remember it. So there's something called congenital adrenal hyperplasia. So there's extra growth of the adrenal glands, and I call this a primary adrenal insufficiency. I don't know if officially it's going to be categorized there, but at the very least, the aldosterone and cortisone levels are going to be lower. So that's why I put it there. But the androgen effects are accentuated there, and they're going to be diminished in partial androgen insensitivity syndrome and absent entirely in complete androgen insensitivity syndrome. So what would this do in XY males? So if I have CAH, basically you're going to have whatever the androgens you had, you're going to have more of them. The effects are going to be more. So puberty is going to start at an earlier age because you're going to get that testosterone surge earlier. Remember that the testosterone is necessary for the external, internal genitalia development. And so this is going to cause an ambiguous genitalia. So the penis is going to be an enlarged clitoris, and the scrotum is effectively going to be the fused labia. And you can see this here with the fused labia and the sort of enlarged clitoris penis hybrid. And then the complete androgen insensitivity syndrome is going to be, and there are degrees of this, but if it's complete insensitive, then it's going to be external female genitalia. Female is the default option. And there will actually be internal testes rather than ovaries, because that really just has to do with having a Y chromosome, having the SRY gene. So in XX females, congenital adrenal hyperplasia is going to cause ambiguous genitalia or male genitalia, because again, if you fertilize these primitive precursor structures with testosterone, they will slant male. And so if a female has or adrenal cortex pumping out too much testosterone. This can cause ambiguous genitalia if there's a little bit, or male genitalia if there's a lot of it. Again, though, having testes requires the SRY gene on the Y chromosome, and assuming there was no, abnormal translocation or anything like that, the XX should just have the ovaries, not the testes. All right, this is a fun, complicated picture, which you'll need to know eventually. I don't actually think it's super high yield to know everything for now. We're really just going to break it down to this. So cholesterol gets converted into pregnenolone and progesterone with the help of ACTH. That's what causes the adrenal cortex to swell, and why we have a large adrenal cortex and, in certain of the syndromes we saw. We have this 21 hydroxylase and 11 hydroxylase, which make aldosterone, and the same thing over here, actually, they make cortisol, but you need to have a 17 to push it to the right. And then this is a 17-20 lyase, which we can ignore to make androgens. But we're going to come back to this. So there's 3 types of congenital adrenal hyperplasias: 17 hydroxylase deficiency, 21, and 11. So let's just imagine what would happen if I had a 17 hydroxylase deficiency. It looks like I can't get to the cortisol and the androgens. So I should have lower levels of those and higher levels of aldosterone. What if I have a 21 hydroxylase deficiency? I can't get all the way to aldosterone, and I can't get all the way to cortisol, which is what we previously talked about. So we're going to have low levels of those, and then you're going to have high levels of androgens. What happens if you have 11 hydroxylase deficiency? It's kind of the same thing, except there is a little intermediate called 11 hydroxydecorticosterone, which actually kind of mimics aldosterone. So let's go ahead and look at this. Like we just said, the cortisone and testosterone are down, aldosterone's up. Cortisone and aldosterone are down, and the androgens are up for the 21. And the 11 is very similar to the 21, except that we have this 11-deoxycorticosterone that mimics aldosterone. Now, what are the effects of all these? We already know everything. You really should just be able to put it together. Aldosterone is going to, if you have more aldosterone, you're going to have higher blood sugar, higher blood pressure, lower potassium, more alkalotic because you're pushing all the H plus out, the opposite of your aldosterone deficient. What if you are cortisol deficient? You're going to be hypoglycemic. What if you have high levels of cortisol? Well, then you're going to be hyperglycemic. You're going to be predisposed to diabetes and the weird, the abnormal fat distribution and the immune suppression and the osteoporosis. And for androgens, well, if you're a male and you have extra androgens, maybe precocious puberty. If you're a female and you have extra androgens, you might have ambiguous genitalia, or you might even have external male genitalia. But remember, you will lack typically testes, and you'll have ovaries nevertheless. So cholesterol can also contribute to bile salts. Remember that bile salts is the main but not only component of bile. So bile is generated by the liver, stored in the gallbladder, and its job is to help grab onto fats and then bring them into solution so that they can be digested by pancreatic and small intestine enzymes. So it's amphipathic, so it can grab onto a polar water molecule and then like a non-polar fat molecule. And we sort of see a little picture of this here and a example here where we're really causing oil and water, two things that are typically not miscible, to mix when we put in a soap or really a bile-like structure there. This is necessary for the absorption of fats. Otherwise, you get steatorrhea, which is really just fatty poop. It's also necessary to absorb vitamins A, D, E, K, which are our non-polar hormones. So cholesterol is, as we said, is the precursor. 7-alpha-hydroxylase is the first and most important enzyme. It's the rate-limiting step to make 7-hydroxycholesterol. This can then be converted into either cholic acid or chenodeoxycholic acid. These are then going to be conjugated with either glycine or randomly taurine. And so we kind of have these 1, 2, 3, 4 different options. I don't think you really need to know anything just about why they're different. I certainly don't know. But these are the primary bile acids that are made in the liver. Once they get into the small intestine, the bacteria are now going to take off the 7-hydroxyl group. They are now called secondary bile acids. So this is now deoxycholic acid and lithocholic acid. So though I wouldn't know the difference between, what does the glycine do versus the toluene, or what's cholic versus deoxycholic, I would know that the deoxycholic and lithocholic in the intestines have had the bacteria take off the 7-hydroxyl group. So something called enterohepatic circulation. So the bile is made in the liver, it goes to the intestines, and then it's reabsorbed. And it goes right back to the liver. So entero as in like the intestines, and then hepatic as in the liver. So it's just doing this very small little cycle, this very small loop. And as we just said, just a little recap, we're going to make cholesterol into 7-cholesterol, and then make it into cholic or deoxycholic, and then we can conjugate it with a taurine or a glycine. We're going to it's going to be pushed through the common hepatic duct, stored in the gallbladder, and then there's a cystic duct here and a common bile duct and the sphincter of Oddi, where it's now pushed into the intestines, where it ideally is going to help us. Fat is like that group of friends who comes to the party and they're all sticking together and they're not socializing with anybody. So the bile is going to come and it's going to emulsify them and cause them all to separate and interact with other people at the party. 95% of bile is recycled. A small amount of it, though, will be excreted in the feces. So vast majority is going to be reabsorbed. We mentioned earlier, if it's not working, you're going to get steatorrhea. So this is going to be oily, smelly, fat typically floats, so it's going to be floating on the top of the toilet, poop, and ADEK. So if you have bile issues, vision, osteoporosis, vitamin E is an antioxidant, so specifically for membrane. So it's going to be really important in red blood cells, cause hemolytic anemia, and also cause peripheral neuropathy because of all of the myelin. And then vitamin K, remember K for coagulation, you'll have easy bruising and bleeding. So we just talked about this, but let's now, it's an important medication called cholestyramine. So this is a bile acid sequestrant. It just grabs onto bile and it doesn't let it get reabsorbed in the small intestines here. So notice the difference. Here's one and here's several. So it's less of them are going here and more of them are going here. And also look at our number. Our number was about 5%. Now 20% are excreted. So why would we do this? Because I have high cholesterol. If I have high cholesterol and I'm now excreting way more bile into the toilet, well, that's going to go ahead and upregulate which enzyme? 7-alpha hydroxylase, whose job it is to turn cholesterol effectively into bile, the bile salts. So this whole process is just going to upregulate this. So we're going to lose more cholesterol because we're turning it into bile. Why are we making more bile? Because we're excreting more bile. Why are we excreting more bile? Because we have this sequestrant, which is not allowing it to be reabsorbed. So when it is reabsorbed, we do reabsorb a little bit of primary and secondaries. Antibiotics will kill the GI bacteria, which means that we should have less secondary bile acids being reabsorbed, though they have a similar potency as primary bile acids. This is just something they occasionally ask. And you're going to have less bile if you have less cholesterol, or the synthesis of cholesterol is down. Maybe you're taking a statin inhibiting HMG-CoA reductase, or maybe you have a 7-alpha hydroxylase deficiency issue where you're having a hard time, with the rate limiting important step in bile salt production. We can also, if we have issues with the bile, either too much cholesterol, too much bilirubin, we can get something called a gallstone. Cholelithiasis is the formation of gallstones. These are really just precipitated bile. And so, I must have said it a million times, so let's go ahead and take a look. Here's bile. Bile is actually mostly water, but this 5% solute is obviously very important. So we go ahead and look at this. As promised, most of it is bile acids. So that's the, we have them over here. That is our, that is a glycocholic acid, a taurocholic acid, glycochenodeoxycholic acid, or taurochenodeoxycholic acid. So that is our 61% of the 5%. But cholesterol and bilirubin are going to be quite important. So these are really going to be the features that are causing the precipitation, the cholesterol and the bilirubin. So if we have too much cholesterol, and this actually accounts for a majority of the gallstones, This is going to be for obese individuals, so they have too much cholesterol. Women have excess of estrogen, and this is also going to cause too much cholesterol. These are going to be these yellow ones right over here. Now, if you have too much bilirubin, you might have this if you have bilirubin is the breakdown product of heme. So if you have chronic hemolysis, you're going to have too much bilirubin. Or if you have cirrhosis and your body just can't handle and process and excrete the bilirubin, which we'll talk about soon, this also is going to increase the amount of bilirubin we have. And too much bilirubin can, again, cause this to precipitate into a nice stone-like thing, which blocks the bile from getting through. Okay, so we just saw that bilirubin is a small but important component of bile. Sometimes it's responsible, if it's too much, for forming bilirubin stones. Will that be a case where we have hemolytic anemia? Heme, blood, lytic, lysing, breaking. So red blood cells are exploding like this little gusher here, spilling out a lot of heme. This heme is broken down into bilirubin, and then that can cause jaundice if there's too much. So yeah, the real question is, how do we process these heme molecules, these protoporphyrin rings and iron? The iron is stored in liver and bone marrow. These are two places that are actually going to be producing heme, which we'll talk about down the road. And the iron is stored in ferritin, and then the ferritin, kind of like a Russian doll scenario, is then stored in hemosiderin. And in actuality, it's not a Russian doll, because Russian doll is 1-to-1. It's more like, the hundreds of irons in a ferritin and lots of ferritins in a hemosiderin. Also note that most of your body's iron is recycled. So we don't actually, I think, absorb that much iron from our diet. So if you're slowly leaking out a little bit, which might be the case if you have like a GI cancer or something, that's actually problematic for many reasons, but one of which is you're losing this iron, which you desperately need, and you're going to get a microcytic anemia with hemosiderin rings, which we'll talk about. So the iron, talked about that. So that the heme is broken down, ideally in macrophage in the spleen. That would be extravascular, outside of like the main bits of the blood. We'll see what happens when we have intravascular in a bit as well. But so this is where we break it down. Iron goes out in the blood, stored over here. Check. All right. So now to the important stuff. The heme is converted via heme oxygenase in the macrophage into biliverdin, which is green. Heme is kind of like reddish. And then biliverdin reductase converts into bilirubin, which is sometimes yellow, sometimes kind of brown. And we'll actually see both of these colors come up later. And so this is where if you get a bruise and someone smacks you real hard and you have a bunch of internal bleeding, well, that blood is getting broken down. I guess that's intravascular in the actual blood vessels. It's getting broken down in real time by macrophages, and it's giving this nice, pretty little color of dark red and kind of greenish and yellow. Let's recap it also a little bit more. So heme, so it's not just hemolysis, red blood cells last every 120 days, and it's like the most abundant cell in your body. So this is going on whether just normal or pathological. So the heme is broken down, hopefully in the spleen, into bilirubin. This bilirubin is then transferred on an albumin into the liver. Now, let's pause and note that if you did have excess intravascular hemolysis, which there's a lot of different ways you can have that, it's carried via haptoglobin to the liver. We have macrophages in the liver called Kupffer cells, and these are going to break these down just like we did in the spleen into bilirubin. So either way, we're getting bilirubin to the liver. Bilirubin now, as we mentioned, it's not particularly water soluble, so it needs to be conjugated if it wants to be easily excreted from our body. So UDP glucuronyl transferase is going to add a glucuronic acid to bilirubin. Now it's water soluble. It's said to be conjugated as well, and we now secrete this into our bile and goes into our intestines. Bacteria are going to convert it into urobilinogen. Like 20% of this is reabsorbed, so it's going to be an enterohepatic cycle. Some of it, though, is going to go to the kidney. We're going to pee it out. And before it gets peed out, it gets converted into urobilin, which actually has this yellow color, and that's why our urine is yellow. And the rest of it, the majority, is going to be converted into stercobilin, which is like a dark brown and gives poop its famous brown color. So how can we get hemolysis? A bunch of different ways, and you don't need to know really any of these, but just, you've seen some of them, right? G6PD deficiency, you can't do the pentose phosphate pathway, and so you can't get NADPH, and you can't regenerate, your glutathiones, you're prone to oxidation, hemolysis. Sickle cell and thalassemias, you can get hemolysis. You can get hemolysis from malaria, lots of different types. So lots of different ways that red blood cells can explode, in addition to the fact that they just do this every 120 days all the time. But as we mentioned, there's also, we can think of it as intravascular, so literally in the blood vessel, and extravascular, which is not, nope, this is backwards. That's less ideal. This is more ideal. We'd rather have them broken down in the spleen. That's the way to go. So they should be broken down in the spleen, ideally. So just to really picture this, if we are in the extravascular, they're broken down here quite nicely into unconjugated rubin. They're put on the back of an albumin. They're sent over here to the liver, where they can be converted to conjugated bilirubin and then put into bile, which is put into the intestines. The iron does go to the, via, whenever iron's going through the blood, it's going through transferrin. And it's weird. It goes, from the spleen to the liver. Some of it's stored in the liver, and then the rest of it is stored in ferritin, which is stored in hemosiderin, and then the rest of it is sent back, again, via a transferrin to the bone marrow, where we're going to store it there. And if you just think about why would we want iron in the bone marrow, well, we're going to be making heme groups for erythropoiesis, making red blood cells. More on that later. So extravascular, I guess this is intravascular. It can be extravascular because some of it could potentially be sent to the spleen. But if a red blood cell just breaks down in the middle of a blood vessel, free hemoglobin. Now, if it's just a little bit of hemolysis that's intravascular, well, it's going to get picked up by haptoglobin, and it goes to the spleen, and the rest is history. We've talked about that. But if it's a lot of intravascular hemolysis, whether I got kicked by a horse or whether I got like really, really severe sickle cell and low oxygen environment, if there's too much hemoglobin, it kind of overloads the kidney, and some of it does make its way through, even though it's not particularly water soluble, and it hemoglobinuria, and you're going to have red urine, blood in your urine, really. So whether it is intravascular or extravascular or G6PD or sickle cell, blah, blah, blah. So whether it's too much hemolysis or it's just the fact that we can't handle maybe everything works perfectly, and it's just that the bilirubin, the unconjugated bilirubin from the spleen brings it to the liver, and the liver just freaks out and can't do its job for whatever reason. We'll talk about that. You're going to have a buildup of bilirubin in the body. Too much bilirubin is called jaundice, and jaundice is yellow. This is jaundice. This is not jaundice. The most useful way to think about jaundice is whether it is conjugated, called direct just because scientists once could directly measure it, or unconjugated, and I guess that was an indirect measurement. And again, we see more pictures of jaundice. It has a particularly high affinity for the eyes, the elastin and the sclera binds to it quite tightly. So unconjugated versus conjugated. We really already talked about this. Just to keep it really simple, everything before the liver is unconjugated. Once it gets into the liver and it interacts with UDP, glucuronosol transferase, it is now conjugated. So before unconjugated, after conjugated. And ideally, this flow should only go one way. We will see actually a couple cases where it goes backwards. We have conjugated going from the bottom half of the screen to the top half of the screen, which is not good. Ugh. All right, so don't freak out, but maybe freak out a little bit. You really have to know all of these, but they're not as bad as they seem. So all the different ways we can get jaundice. Again, I think the most useful framing is unconjugated versus conjugated. So the unconjugated, for the most part, it is that the UGT is slower processing, but I guess that's not all of it. So hemolytic, I guess, is an immediate violation of that rule. Hemolytic, we've already talked about it. This is just way too much red blood cell breakdown, and you're overloading the liver. So the liver can only take in so much bilirubin at a particular time. And so I'm just building up all of these. Can I change the color of this? Yes. All right, so I'm just building up all of these unconjugated bilirubins because they're waiting. They're waiting in line to go in here, but it's just there's too much, and the liver can't process them fast enough. And so what do I have a buildup of? I have a buildup of unconjugated bilirubin. Gilbert, so actually 5% of the population, is 1 in 20 people has Gilbert syndrome. This is where the UGT just doesn't work as well. And so usually actually these people are completely asymptomatic. Um, Perhaps if they have a large hemolytic stress, if they're eating a lot of fava beans and they get malaria or something, maybe they'll get a buildup of unconjugated bilirubin a little bit faster than the liver can take it. But again, they're normally fine. So Crigler-Najjar, now there's types 1 and 2, and maybe it's worth knowing those differences, but I didn't feel like talking about it. You just don't have really any UGT. And so this is obviously going to be much more severe, and it's going to present early in life. You're going to have babies and kids with jaundice and something called kernicterus, where it can get into the brain. And then that is not to be confused with physiological neonatal jaundice. So there's a difference between saying a baby has jaundice when they're a kid and a baby has physiological neonatal jaundice. So 50% of all kids, I saw some studies saying even like 60% of kids are born with jaundice in the first 2 weeks of life. And this is a combination of two things. Their livers are underdeveloped, so they don't have much UGT going on. And the fetal red blood cells, out with the old, in with the new, are being broken down by macrophages to make like newer red blood cells that express different types of hemoglobin. So getting rid of the old red blood cells and making way for the new red blood cells. And so this is just going to be extra bilirubin to process, in addition to the fact that we can't really process it because our liver is just a itty witty bitty little baby thing. And so you're going to have too much unconjugated bilirubin. It does typically self-resolve in a couple of weeks, though. So only about 5% of the babies actually need treatment and care because the unconjugated bilirubin is at a sufficiently high level. So conjugated bilirubin. So it can be a couple different reasons for this, but maybe we'll just start with the Dubin and Johnson one. So there is a little protein transport to get from the liver into the GI tract, and it's MRP2. Now in Dubin-Johnson, this is not functioning well. And so if that's not functioning well, I'm going to have a buildup, I guess I have to change my color now, of conjugated bilirubin. It's already gotten to the liver, it's already been conjugated, but it's going to start building up. And it can't go this way because the MRP2 is blocked. And so what happens is we get this MRP3, which is a retrograde transport protein, gets upregulated, and it starts sending this conjugated stuff over here. And now I have conjugated bilirubin in my blood. Rotor is effectively the same thing. Instead of MRP2, it's a different carrier protein that's screwed up, and I think the same thing happens. So treat them interchangeably. The only difference is that, for whatever reason that I don't understand, Dubin-Johnson is a black liver. And then the rotor, I guess, will just look normal. So obstructive jaundice. Obstructive jaundice now is if you have a gallstone, whether it's cholesterol is 80%, and I think it was the bilirubin one was 20%, or you could have like a pancreatic tumor. And so you can kind of see pictures of these here. So here's our pancreatic tumor blocking. Here we could have something there. You could also have something there. These are going to block. So let's look at this picture over here now. So we have unconjugated bilirubin, unconjugated. It comes in here and it's unconjugated, and then the UGT is going to convert it to conjugated bilirubin, and it's going to go through the MRP2, and it's just fine. So again, we're talking about obstructive jaundice here. And it's traveling. Now there's a block. There's a block because there is a pancreatic tumor or a some sort of gallstone. And so the conjugated bilirubin just builds up, and creates this enormous pressure, and it just pushes all the way back through here. And now the thing about this pressure is it doesn't just push the conjugated bilirubin backwards. It pushes bile in general backwards, which means that cholesterol is going backwards as well. Cholesterol, we saw, was a component of bile. So everything in bile is going to go backwards. The cholesterol in particular, though, can contribute to hypercholesterolemia, so too much cholesterol in the blood. This contributes to things like xanthomas, where we have like fatty deposition in the skin. It also contributes to pruritus. It deposits in the skin and it makes people itchy. Pruritus, just fancy pants talk for being itchy. We then have mixed. Let me get rid of this. Go away. Then we also have mixed jaundice. So this can be hepatitis or cirrhosis. So, if you get a viral infection or you're drinking too much and, you just start destroying your liver, this can actually increase both types. So let's go back to this fun little drawing. So if I have a bunch of, this guy's dead and this guy's dead, well, that means I don't have as many like functioning liver cells to process my bilirubin. So I'm going to get more and more and more unconjugated bilirubins. On the other hand, though, if we have these dead hepatocytes, it's not just that they can't process. We're also going to be able to, these tight junctions, they're just decaying and falling away. So any scaffolding they had, the extracellular matrix is going to be not maintained as well. So we're going to really just have what we saw with the Dubin-Johnson, rotor, and obstructive, this backflow of bile. And so that's going to increase the conjugated bilirubin in the blood as well. So all of these conjugated bilirubin values are going up. So this can also cause pruritus, hypercholesterolemia, and xanthomas. I hate this thing. I really wish it would go away. There we go. Sorry. So another way that we can categorize this, you might see, is prehepatic. This is really just too much hemolysis. Intrahepatic. Now, I don't like this because it just really puts all the congenital disorders together. And as we saw, something like Dubin-Johnson versus Gilbert is going to be quite different. Nevertheless, sometimes people call these intrahepatic. And extrahepatic, which is just the gallstones and pancreatic cancers and whatnot. Again, I prefer the conjugated versus unconjugated framing. So any type of neonatal jaundice could potentially lead to kernicterus. So this is where the bilirubin is getting into the blood, passing the blood-brain barrier, and it's accumulating in the basal ganglia. Phototherapy. So some smart nurse noticed that the babies, I guess, who are sitting, in the nursery in the hospital, closest to the window and like in the jaundice ward or whatever, they seem to do better than the other babies. She just, over the course of her career, she noticed that, so I guess they figured out that. Normally bilirubin is processed here and it becomes glucuronidated, it's conjugated, it's water soluble, it can be excreted. But in a case where I have defective UGT, now bilirubin, if I have phototherapy, this light is going to cause it to become a photoisomer. And the photoisomer doesn't need to get processed by UGT. It just is a little bit more water soluble. So that is how the phototherapy works. Colors. All right. So if fecal matter is pale, it probably means that bile duct is blocked. Yellow might mean that you just have too much fat, and there can be a little bit of an overlap here. Urine should be yellow, and that's because urobilin. And if it's brown, that's going to be because of bilirubin, typically conjugated bilirubin. And if it's red, it's just going to be, might be because you have too much heme straight up in there. And we'll come back to this in a second. So this is a good picture to look at, understand, digest. Where does the iron go? How does everything get broken down? But we're really just interested in this. So this is just really just a recap of everything we just said. If you have too much hemolysis, then some of the heme will make its way into the kidney and it is red and it makes your urine red. Bilirubin is kind of yellow, kind of dark. It depends. So, it's going to be glucuronidated. It's put in the intestines. Bacteria messes with it. It comes urobilinogen, which becomes urobilin, which goes in the kidney. That is yellow. Stereocobilin is going to be brown, and that goes in the fecal matter. Sometimes the reason I made that this brown and yellow is because we saw in the obstructive, Dubin-Johnson, rotor, hepatic, like cirrhosis, the conjugated actually, it doesn't actually move from here. Technically, the conjugated is going to move from here. It's going to move from here into the blood, and then actually the conjugated bilirubin can get into the kidneys, and that actually creates kind of like a dark reddish, dark brown color of the urine. So more on poo-poo and pee-pee. This is really important. It's actually really high yield. So in the stool, stereocobilin makes it dark brown. So let's look at something like hemolytic anemia. We have a lot of bile moving through because there's a ton of unconjugated bilirubin and it's making the liver process it as fast as it can. So we might have a little bit more sterocobalinin, so we should have dark bowel movements. If you have something like Gilbert or Dubin-Johnson or Rotor, or obstructive or hepatitis, or actually most of them, honestly, regardless of the cause, whether it's UGT is not working very well, or it just can't get through because there's an obstruction, or the protein to shuttle them from the liver to the GI is not working, or you have hepatitis, any of these, the end result is we're not getting bile into the GI. So we're not getting sterocobalin in our stool, so we're going to have pale, fatty bowel movements. The urine, we said urobilin gives urine its characteristic yellow appearance. So hemolytic anemia, we should have like a lot more urobilin, and that's going to make it particularly yellow. The only issue with this, though, is that for hemolytic anemia, we might also be having too much heme in the blood, and the heme is also going to go into the kidneys. Excuse me. And I guess heme, the rock, paper, scissors between heme and urobilin to who has a stronger color. I guess it's heme. So, or in it, and this is being an impossible question for them to really ask you, but I guess it's the red and the yellow. It's going to be kind of like a dark reddish, but so I would just keep that in mind. It theoretically could be either, though I would skew towards saying it's red if you have a hemolysis issue. Now, conjugated bilirubin gives it a dark red appearance, not like the red of, I guess, like heme. It's a slightly different, darkish red, dark brown. And this can be the case where we have a obstruction or Dubin-Johnson or something, and we said that it flows backwards. Again, not from the gut to the liver. Technically, it goes backwards through here, right? Again, remember, MRP2 is broken down into MRP3, and then it can go from the liver to the bloodstream, and from the bloodstream, it goes in the kidney. That makes it like a dark red urine. Again, I'm having a hard time showing it here, but the color is slightly different. If we can kind of see here. I think we're looking at like red versus like reddish brown. Maybe we'll see it in a second as well. Actually, I don't think I have a picture. They'll make it kind of clear, I think, from the vignette. So for these are all the different types. Hemolytic, we have too much hemolysis for whatever reason. You're going to have typically more unconjugated. But you are still stressing the liver, and more sterocobalin means that you're going to have dark brown. And the urine color, this depends, right? We have more urobilin coming in, but it also depends how much of the heme is making its way to the kidney versus getting shuttled via haptoglobin to the spleen. We can just say dark red for the most part. Gilbert, less UGT, typically asymptomatic unless you're really, even a lot of fava beans, a lot of unconjugated because there's no backflow. The only time you have conjugated is if they're backflow typically. And so there's just maybe a small line. You might have pale stool. Again, it might be normal, but it could be pale if you're stressed and just not enough is getting through. And the urine color, maybe it's a little bit clear. Maybe you have a little bit less urobilin. But again, these are really going to depend. So these are some of the fringe cases. Crigler-Najjar, there's no UGT. This is unconjugated, just like Gilbert. Maybe it's a little bit more severe. Again, we're having a hard time getting the bilirubin to be conjugated because UGT isn't working. And so we should have no sterocobalin, meaning we should have pale, fatty steatorrhea. And the urine, again, we're not processing it through. Urobilinogen becomes sterocobalin, which makes stool black, and becomes urobilin, which makes urine yellow. So this should also be a little kind of clearish, not as yellow. Neonatal physiological jaundice. Again, this one's tricky because it's like half hemolysis related because we're breaking down a lot of the fetal hemoglobin to make room for the adult hemoglobin. But it's also the fact that the liver is kind of immature, so we don't really have a lot of UGT going on. And we have a lot of unconjugated, and it becomes pale because the UGT just isn't working enough to make conjugated bilirubin to become urobilinogen to become sterocobalin. And this is tricky. Dark yellowish, dark red. I've seen different things online. I would just kind of say it's a mix between, the fact that there's maybe a little bit of heme because there's a lot of hemolysis, and it's going to be pretty yellow because we're really pushing things through. So Dubin-Johnson rotor. We can't move it from the liver to the GI because of the MRP2 is defective or some other protein for the rotor. So it moves backwards. Remember, the Dubin-Johnson is black versus rotor, the liver. So this is conjugated because it's going backwards. But in this case, though, remember, it's just the conjugated bilirubin that's going backwards, not the whole bile. The stool is going to be pale because no stereocobalin, and the urine is going to be dark brown, specifically because we have a lot of this conjugated bilirubin here going backwards, retrograde flow to the blood, to the kidneys. Obstructive is pretty much the exact same thing in terms of like what we see over here. The difference is just that there's like a gallstone or pancreatic tumor, and that's pushing not just the conjugated bilirubin back, but all of the bile, which can cause pruritus and hypercholesterolemia and xanthomas. Hepatitis and cirrhosis, I said conjugated, but it could be conjugated and unconjugated, could be increased, right? Unconjugated because our hepatic cells are just crappy, and sometimes they put a time on this. They say earlier it's going to be unconjugated, and later it's going to be conjugated. I just think of it as both. Unconjugated because we're not processing the bilirubin that much, so more unconjugated. And then conjugated because, well, there will be some retrograde flow if we have a complete breakdown in the cellular and tissue architecture, so that there's really no dam. There's no there's no barrier preventing the bile and the bile ducts from flowing backwards through the liver and into because the liver's just dead and shitty, backwards into the blood, where again same thing happens. So now we have conjugated and unconjugated up. If we're not getting as much through, it might make this stool pale. And if you are pushing out, if you conjugated from the blood to the kidneys, that might make the urine dark brown. Okay, so we saw what happens with heme breakdown, right? We get bilirubin, too much of that, you get jaundice. Let's look at the other end of the spectrum, heme synthesis. And you get something called a porphyria that develops if there's any issue with the heme synthesis pathway. And if there's an issue with the heme synthesis pathway, well, protoporphyrin, it needs to be included and combined with iron to make a fully functional heme, to make a hemoglobin, to make a fully functional erythrocyte. So if you have a porphyria where you're not producing heme correctly, you're probably having a huge increase in your iron, and you're probably not getting effective erythrocytes. So you're going to get an anemia. And sideroblastic, sidero really just means iron. So you get these iron-laden erythrocyte type anemias. So the heme synthesis pathway, it's kind of a lot, but so you can remember the mnemonic, get some additional points having understood the correct pathway for heme. So this is glycine, succinyl-CoA, aminolevulinic acid, porphobilinogen, hydroxymethylbilane, uroporphyrinogen, coproporphyrinogen, protoporphyrin, and heme. It's a mouthful, but I promise you it's not as bad as it seems as we move through everything. So we're going to make it a little bit simpler. So to really start off to understand the pathology of the different types of porphyrias, remember that this pathway is going to be on in both the liver and the bone marrow. Why the liver? Because cytochrome P450 requires heme as a prostatic group. Why the bone marrow? Well, that one's easy, right? Bone marrow is going to do erythropoiesis. This makes red blood cells. Red blood cells need heme to make hemoglobin. So the porphyria is going to develop, as we said, whenever there's a hiccup in the heme synthesis pathway. So this really just helps you understand the symptoms. So your question should be: is it the liver? Is the bone marrow, or does it affect both types of the heme synthesis pathway? And if it's both, actually, it tends to be the bone marrow issues a little bit more. So the red blood cells, in other words, the bone marrow, we're going to have less hemoglobin, and this is going to cause an anemia, like we said, right? You're not making heme, so you can't make hemoglobin. Your red blood cells stink. It's a microcytic anemia. The red blood cells are particularly small, and it's sidero, just means they are iron laden. Why iron laden? Because again, you have a bunch of iron in your red blood cell. You're supposed to, combine it with the protoporphyrin, and if you can't, then you just have a bunch of iron, and so it's gonna start aggregating. Now in the liver, the issue is going to have less cytochrome P450 to detoxify things. Additionally, you'll get toxic intermediates just literally of the heme pathway. Heme itself is not toxic, but the intermediates are toxic, which we'll see. So which toxic intermediates is going to be one question, and this can also we can also divide these liver related ones into whether it's acute or chronic. And because we're looking at a much, there's a lot of different types of porphyrias. I think we're really only dealing with two. So we're going to be looking at one acute version and one chronic one. So the acute porphyria, we're just going to treat with heme. Also randomly glucose. So heme should make sense, really. If we're starting with succinyl-CoA and the end product is heme, this works on a negative feedback where once we have enough heme, it's going to go ahead and stop the whole process of making heme. So if the issue is that I'm, generating too much, too much of this guy right here, right? I have too much of this. I have this acute porphyria. If we give a lot of heme, we're going to ramp down the production so that we're going to have less of this. That's going to treat it a little bit. So that kind of makes sense. The succinyl-CoA, I read online an evolutionary argument that I think stinks. It doesn't really make sense to me, but it makes sense superficially. But if you think about it, it seems a little wonky. The idea is that if you give somebody glucose, the glucose eventually is going to be combined with the succinyl-CoA in the Krebs cycle, and so that would get rid of the precursor, and or the succinyl-CoA would want to be preserved. Didn't I'm not articulating well, but from what I even understood of it, it didn't really make sense. But if that helps at all, you can just thinking that if you had a lot of glucose, you would want to preserve your succinyl-CoA for the Krebs cycle and not use it here. Whatever sticks. That works for me, at least for remembering it. Okay, anyways, let's keep this train moving. Chronic, regular phlebotomy is just draining of the blood, is going to get rid of the excess iron, excess heme intermediates. Also sun avoidance, and we'll see why in a few slides. And now both of these, this is quite important, are going to be exacerbated by alcohol and other P450 inducers. Alcohol is probably the most common one. Remember that alcohol can be processed by 3 different pathways. One of them is right here is a cytochrome P450. So it induces transcription and production of cytochrome P450. So that means if we have more of this, we are going to lose heme because it is being incorporated in those cytochrome P450s. That means we have less negative feedback. And so whatever intermediates we had are just going to get more and more and more and more and more. Additionally, we saw that, in some cases, ideally, the heme is broken down in like a spleen, but it could be broken down to the liver by Kupffer cells. And if we're inducing cytochrome P450, we're really inducing the breakdown of heme itself. And so breaking down more heme because we're inducing cytochrome P450s further lowers the level, which is going to further cut back on the negative feedback. In addition to whether it's liver or bone marrow, we can also ask, why does the defect exist? So there's two more different ways we can categorize it. If it's genetic or enzymatic, here we have X-linked sideroblastic anemia. There's a lot of different types of sideroblastic anemia. Sideroblastic anemia just means anemia where you have a bunch of iron. This is just the only one that's X-linked, hence the name. It is this enzyme, which we will come back to, and this, though, specifically is just in the bone marrow. This is actually the only enzymatic deficiency that we'll talk about that is bone marrow specific, and that is going to be important for these symptoms. Acute intermittent porphyria, this is going to be porphobilinogen deaminase in the liver, and then porphyria cutanea tarda. This is going to be uroporphyrinogen decarboxylase in the liver. Then we have acquired causes. So B6 deficiency or lead poisoning. So this is going to affect both the liver and the red blood cell, but it's going to have a larger effect in the bone marrow. If I say red blood cell, I mean bone marrow. So X-linked sideroblastic anemia. So it is this first enzyme that is deficient, and you actually have ALA1 and ALA2, and I forget which one's which, but it's only affecting the one that is in the bone marrow. So your liver's fine, but your red blood cells stink. They're not making enough iron, and so you get these little iron rings, these iron things. I thought it was like the rocks that make up the rings around Saturn. So these rocks make a little ring, hence the name ringed sideroblast. You also have a nucleus. You're not supposed to have a nucleus in your red blood cells. So there's well, I guess technically this isn't a bone marrow, but nevertheless, there's nucleus, the red blood cells are around it. It doesn't always have to be a full ring. It could be like a third of a ring as well. So they're not always going to look so like perfect. Like you can kind of see here, this one's pretty much like a full one, but this one's only about half, but it still counts as a ringed sideroblast. You also, anytime your red blood cells stink, even if it's not even just specific to this disorder, specific to any anemia where the red blood cell production is shitty, you get these clumps of RNA ribosomes and mitochondria sometimes too, and this is called basophilic stippling. So just ferritin, remember, holds the iron. Hemosiderin can hold ferritin, and then a siderosome is just going to be hemosiderin-filled lysosomal body. And yeah, so we've actually been through a couple of different red blood cell histology things. So just to keep everything straight, a Howell-Jolly body, anytime you have a shitty spleen and it's, nucleated red blood cells should not be in circulation. If they are, the macrophages try to kill them and take them out of circulation. And if they miss one, then this is what we see. This is the nucleated red blood cell, a Howell-Jolly body. Heinz body we saw when we had like hemoglobin H, we have enough hemoglobin that it starts precipitating and it forms a Heinz body. Basophilic stippling, we just said really any malformed red blood cell, not just the iron-related ones. And the siderocytes are the ones that have an excess of iron. You need something called a Prussian blue stain to visualize these. And yeah, this is the actual pictures of all four of them. Acute intermittent porphyria. So this is porphobilinogen deaminase deficiency, specifically in the liver. So porphobilinogen accumulates in the body. This is the toxic intermediate. So this is neurotoxic specifically. This was going to cause psych symptoms, peripheral neuropathy, and gastric distress due to tampering with the autonomic nerves. And I just thought of like porphyria and port. You have port-colored wine, or I guess port-colored urine, because port is like sugary wine. And it's exacerbated. And we should really say precipitated by alcohol. So this is going to be a distinguishing between the acute, really think about the name. This is acute. Like I'm fine most of the time, and then boom, just one day, 1 week, my porphyria really kicks up because I, had a bunch of, had a bender. I had too much alcohol. So it's not just exacerbated. This is really just precipitated by that. And again, the cytochrome P450, one, if this is induced, we need heme to make the cytochrome P450s. That lowers heme. Also, more cytochrome P450s is going to degrade heme itself with the heme oxygenase. That's also going to lower the heme. And if you have less heme, then you have less negative feedback, which means the pathway is going to go into hyperdrive, the heme synthesis pathway. And if it's going into hyperdrive, I'm going to get more intermediates and more toxicity. And the opposite of that is going to be hemin, which is just heme and glucose. The heme is the negative feedback, hooray. The glucose, weirdly, arguably, the body wants to preserve the succinyl-CoA and says, hey, don't put the succinyl-CoA into the heme pathway. We got a bunch of glucose that we need to combine it with. Again, that doesn't really make sense to me because we're in the liver, not a normal cell, but I'll let that one slide. And maybe I'm wrong. Porphyria cutanea tarda, uroporphyrinogen decarboxylase deficiency in the liver. So here, we were previously looking at this one. Now we're looking at this one. So again, things are typically named after their the precursors. So that makes it a little bit easier. But so this is going to increase in the body. And this one, instead of depositing in the nerves, deposits in the skin. Hence the name cutanea, right? Cutaneous. This is the skin related one. It is going to be oxidized by light. So if it gets in the skin, I guess that's fine. But then it gets oxidized. And I've read a couple different things. Some people say it generates free radicals, which maybe it does. Some people say it degranulates mast cells, which maybe it does. In any case, your immune system freaks out and you get these large blisters. And one of the reasons you want to stay away from the sun. So that is actually one of the main treatments here. Stay away from the sun. A lot of people think of vampires for this. Same as the last one, except it's not precipitated. This is always an issue. It's just made worse. It is exacerbated, not necessarily precipitated by alcohol. And you would treat this with phlebotomy and chloroquines. Chloroquines somehow stop the oxidation or calm down the immune system. B6 peroxidine pyridoxine deficiency. It's bone marrow and the liver, but the symptoms are mostly going to be bone marrow related. So we're going to get sideroblastic anemia because we're not making red blood cells. How can we deplete B6 tuberculosis drug isoniazid, oral contraceptives, and again, alcohol, just like we saw with like B1 deficiencies. Inflammation in the gut makes you're not going to absorb vitamins as well. Additionally, you probably don't have the best diet. There might be another reason why alcohol would cause a B6 deficiency, but that's probably enough. You just need to remember that it might cause it. And that's needed for the first step. And you can remember that B6 is needed here, right? Because one of the things about B6 is that it was really good as a transaminase, about like turning amino acids into their derivative products, right? Like, tryptophan into, melatonin or serotonin, or tyrosine into the catecholamines. And here we're seeing glycine being converted into something else. So that's where the B6 comes in. Lead poisoning is going to affect both, but again, the bone marrow symptoms are going to be more important. Anytime they mention somebody lives in an old house, they might be referring to the lead poisoning. Either rust from the pipes, PB I think is plumen for Latin for like plumbing. A lot of people used to use lead for their pipes, and the water runs through it, leaches the lead, and you can drink that. Also, it can be an old paint, and you can breathe in the fumes. So it mimics iron. So this is going to inhibit ferrochelatase, which makes sense. This is the very last step, the one that uses iron. So it makes sense that it might confuse the PB2+. A little bit more random is that it also inhibits ALA dehydratase, which doesn't seem to directly interact with iron. So I don't know why that is, but you're not going to get heme, and if you don't have heme in your bone marrow, you are going to have sideroblastic anemia. And anemia because you're not have enough heme, and sidero because their iron is just sitting there around there saying, what do we do now? The lead, though, so additionally, though, the lead can mimic calcium, and it can deposit itself in joints and bones, and it causes a lot of pain. You also get these really dense metaphyseal lines on an X-ray. You also get these burden lines. The burden lines are shown here. So as the lead's just kind of circulating around. We have all of these bacteria that are good bacteria, and sometimes bad bacteria, this oral flora, which produces sulfur. The sulfur can combine with the lead, and it deposits in the gum to form these lovely burden lines. Also neuro issues, because not only does we need calcium in our bones, but we're also going to need it. Calcium is necessary for vesicle release in the of the neurotransmitters in the presynaptic neuron. So it's also because it mimics calcium. It's allowed through a calcium transporter into the brain. So it's going to cause peripheral neuropathy, but it can also, and more significantly, affect the brain, causing headaches and people to forget things. And for kids, very significantly, developmental issues. Here is a negative correlation between IQ scores and blood lead concentration that is found in children. A little overview. So glycine and succinyl-CoA, B6 and ALA synthase makes aminolevulinic acid. By the way, all of this is happening in the mitochondria. That's actually really important. This first step here, in the last step in the mitochondria. X-linked sideroblastic anemia is just affecting the bone marrow, and so that is really just causing a sideroblastic anemia, hence the name, but there's not really a toxic intermediate that we need to worry about. ALA dehydratase is inhibited by lead, so is ferrochelatase. This is going to cause a sideroblastic anemia, but also it's going to cause issues in the bones and the nerves because calcium is going to be mimicked by lead. We can then look at acute intermittent porphyria. Again, the name acute, it's coming on all of a sudden. It's intermittent. It's not all of the time. So when it does happen, just pop in some hemin and some glucose, and that the negative feedback or the wanting to preserve succinyl-CoA should stop the pathway. But the porphobilinogen makes the urine port wine color, and it is specifically going to deposit in the, it's going to cause like a neurotoxicity, so stomach pain a neuropathy. We can look at cutaneous tarda porphyria, where we have this enzyme deficient. This increases, it's going to deposit in the skin. If it deposits in the skin and interacts with the light, it can become oxidized, causes the immune reaction, and you get all of those blisters. So just stay out of the sun, maybe take a chloroquine, and get a phlebotomy every now and then, and you should be okay. All right, I hope that was helpful. All the best.